welcome to the first set of videos on Descartes. So the reading associated with this video is going to be Descartes, the first 4 sections of Descartes' Discourse on Method. The Discourse on Method was a work that was published in French, and it was meant for a popular audience. Whereas the Meditations, although also in a sense intended for a popular audience, was more intended for a scholarly and scientific and philosophical audience. Now, in these videos, I'm not going to be talking that much about the Discourse on Method. I want you to read it in order to sort of get a sense of how Aristotle's thinking, Descartes' thinking, what his general project looks like. But what I want to do in these videos is give you some of the background, fill in some of the missing picture, right? I mean, we're jumping ahead almost 2,000 years, and a lot happens in between. And so what I want to do in this video is tell you some of the relevant philosophical and especially scientific advances and mathematical advances, tell you about some of the mathematical advances that lay the groundwork for Descartes, that make Descartes possible. So in the shift from the ancient to the modern period, a new question becomes central. So in the ancient period, the central question was, what is there, right? What is the nature of things? What is the nature of reality? And only secondarily did Plato and Aristotle try to answer the question, well, what can we know? How do we know what there is? And in the modern period, the focus shifts. The focus shifts from what is there over to what can we know? What can we know? And the idea is, what's common to many of the modern philosophers is they thought they could establish substantive conclusions through answering this question, what can we know, about reality. So by answering the question, what can we know, they often thought they could figure out things like the nature of the physical world, or the possibility of our knowledge of the existence of God, or the nature of our souls, or whether our wills are free. And so we're going to see all of these things in Descartes. So we're going to see that for Descartes, I mean, he's really the philosopher in which this shift takes place. So we're going to see that through asking after what he can know, he comes to substantive conclusions about the nature of the physical world, our knowledge of the existence of God, the nature of souls, and whether our wills are free. Now, in the shift from the ancient period to the modern period, and in particular, in the shift from the old Aristotelian physics, which we were just looking at, and the old Aristotelian philosophy, to the scientific revolution, and the new mathematical science of Copernicus, Galileo, Bacon, Kepler, Descartes eventually, and eventually Newton. So in the shift between these two paradigms, there are going to be sort of two fronts where the disagreement is taking place and developing. So there are going to be disagreements over astronomy, or the heavenly sphere, the physical world outside of the terrestrial earthly sphere. And then there's going to be disputes over the nature of the fundamental substances here on Earth and earthly motion. So the nature of matter on Earth and motion on Earth. And you can sort of think of Aquinas, who lived from 1225 to 1274, as the sort of culmination of the Aristotelian way of thinking about nature. And so it was really Aquinas who put forward the doctrine that there's nothing in the intellect that wasn't first in the senses. We looked at that back in Aristotle, and there's a way in which, yeah, there's some truth of it in Aristotle, but it really becomes solidified in Aquinas, and Aquinas is really a big proponent of this doctrine, that nothing is in the intellect that was not first in the senses. And so we're going to sort of be using Aquinas's conception of nature as representative of the Aristotelian or what gets called the scholastic or medieval conception of nature. And the reason it gets called the scholastic conception of nature is that it was developed by these monks, these scholars, in responding to Aristotle. And so they spent a lot of time working on Aristotle, thinking about Aristotle's ideas, refining Aristotle's ideas. And the scholastic conception of nature, it's very, very influenced by Aristotle, but it's also subtly different and more refined in various ways. And so Aquinas was the main representative of this. And, you know, we're not going to get too into the details here, but I wanted to introduce the way in which Aquinas and other scholastic philosophers were thinking about astronomy and terrestrial motion. So Ptolemy, towards the end of the ancient period, comes up with the geocentric theory of motion. So the geocentric theory, right, it's geo, where geo means earth, right? So geo is earth, and so the geocentric theory puts earth at the center of the solar system. And so the other heavenly bodies go around the earth, and one of them is going to be the sun. So the sun goes around the earth. The moon, of course, goes around the earth, etc. And so on this theory, the earth was the center of the universe. And this theory had a lot going for it. So first and foremost, right, we're going to be contrasting it with the heliocentric hypothesis developed by Copernicus, which places the sun at the center of the earth, right? So, or the sun at the center of the solar system. So the sun, and then Mercury, and then Venus, and then finally the earth, right? Well, it keeps going, of course. Okay. So why did this Ptolemaic or geocentric theory of heavenly motion, why did that seem like a much better theory for almost 2,000 years or 1,500 years? Why did this seem like such a better theory as compared to Copernicus's theory? Well, I guess 1,500. One thing is, if you thought the earth revolved around the sun, well, there was this question: why doesn't the sun appear? I mean, why is it that the sun appears to go around the earth, right? So, I mean, if you wake up in the morning, the sun rises in the east and it seems to be rotating around the earth. It goes across the top of the sky and it sets in the west, right? So it seems like the sun is rotating around the earth. It doesn't seem like the earth is rotating around the sun. And so that's one thing, one very obvious thing that the geocentric theory had going for it. But another big issue, another big thing that the geocentric theory had going for it was, well, if the earth rotated around the sun, it'd have to be going really fast. And if the earth was rotating around the sun really fast, then you might wonder, why doesn't everything just fly off of the earth, right? Why isn't it that, you know, I mean, the earth has to be going around the sun at like 500 miles a second. So why isn't there this huge wind that just blows everything off the face of the earth? Seems like the geocentric theories got a better account, right? I mean, if the earth is at the center of the universe and it's still, that explains why there isn't some huge wind that blows everything off of the earth. Finally, number 3. So 1, 2, 3. So it appears that the sun goes around the earth, right? That was 1. And the second is that it explains why everything doesn't just fly off the earth. And the third thing the geocentric theory has going for it is it gives really accurate predictions of where the planets are going to be at any given point in the sky. right? So, I mean, astronomers had been making observations of the heavenly bodies for, 1,500 years, roughly, by the time Copernicus came along. And they had really, really, really refined equations that could tell them where a given celestial body, where a given star or planet would be X number of days from now. 5 days from now, 10 days from now, 2 years from now, 10 years from now. And so they could predict with an incredibly high accuracy where the planets would go, what their motions were. So they thought the planets, so on the geocentric theory, the planets didn't move in circular orbits. They moved in these elliptical paths where they did these kind of curlicues in going around one another. So they sort of orbited one another, but then they would do these little loops. And by including those loops in the paths of the celestial bodies, astronomers could come up with incredibly accurate predictions of where the heavenly bodies would be, where the celestial bodies would be. And that, I mean, that's in contrast to Copernicus. So on Copernicus's theory, right, he held that the sun was at the center and Venus and Mars and Earth and all the other planets, all the other celestial bodies rotated around the sun in circles, right? So I didn't draw these circles very accurately, but Copernicus held that the rotations of the planets around the sun were exactly circular. And on this theory, the daily motion of the heavens is an illusion, right? So it's not that the sun is going around the earth every night, right? And every time the sun comes up, well, every time there's a new day, that's because the sun has made another circuit, right? That's an illusion. Rather, according to Copernicus, the earth is rotating on an internal axis, right? So the earth here is actually spinning, and that's creating the illusion of the sun going down and coming up and rotating around the earth, right? So it's actually us on earth that are moving. Further, according to Copernicus's theory, the annual circuit of the sun, so the path that it makes in the heavens, as well as the stranger wanderings of the planets, are also illusory, right? So, they appear to be wandering around in the sky in these elliptical patterns, but that's also an illusion, right? That's due to the Earth slowly orbiting around the sun, and it's turning on this axis, right? So he thought, well, if the Earth turned on the axis and the Earth was spinning around the sun, then that would produce the illusion of these elliptical motions. But problems, right? I mean, we're still faced, so he's explained away one, he's explained away, why it seems like the sun's going around the Earth, but he hasn't explained why objects don't fly off the Earth, or why they don't at least fall on curved paths, right? I mean, why, when you drop something, it doesn't go like this, right? Why it goes straight down rather than going at an angle. I mean, if the Earth was rotating, at 500 miles a second and spinning around the sun incredibly quickly, well, then when you drop something, you'd expect it would sort of fly off in this direction and not go straight down, right? So connected to why don't things fly off this surface of the Earth because of a great wind, there's why do things fall straight down and not on a curved path? And finally, another big problem for Copernicus was that his predictions were way less accurate, right? So he could predict very crudely where celestial bodies would be in the sky. Whoops. But he could not predict nearly as accurately as the geocentric theory, as Ptolemy's theory. And so those were serious problems. And in fact, for a long time, not even serious scientists took Copernicus's theory very seriously. And that all began to change with Galileo Galilei and Johannes Kepler. And we'll come back to how Kepler and Galileo sort of gave Copernicus his footing and made it so that, Copernicus's theory really was clearly a contender and probably a better theory. But before we turn to that, let's return to terrestrial motion, or motion here on Earth. So, according to the scholastic theory of Aquinas, there were four basic elements: earth, air, water, and fire. And so everything that was made up out of these four elements: earth, air, water, and fire. And each of these was qualitatively different, right? I mean, the differences between them were a matter of their qualities. What do I mean by that? Well, earth was hard. Air, was light. It was lighter than earth. It was transparent, right? Transparency is a quality. Fire was hot. Hot was a quality. Hot was a quality. Water, wet. Wetness was a quality, right? And so what distinguished these four elements was their various qualities, whether they were hard, how they smelled, whether they were hot, whether they were wet, right? Those are all qualities, qualitative differences. And this goes along with their each having different essential features, right? So we've seen this a bit already, right? Like fire is essentially hot, water is essentially wet, etc. Right? So they have different essential features that are qualitatively different, that make them what they are. And perhaps most importantly, each of the four basic elements moves to its natural place. So earth is heavier. It is the heaviest element. It's going to sink down when it finds itself surrounded by air. Fire is the lightest element. It's going to move up through air and try to get to the highest place. Air is lighter than water, but heavier than fire. And water is heavier than air, but lighter than earth. And so each of these four elements is always trying to move towards its natural resting place, right? It's always trying to get to a resting spot. And this explains some kinds of terrestrial motion, some kinds of earthly motion extremely well, right? So think about bubbles floating upwards in water, or stones falling down in water, right? This does a great job at that, right? Bubbles are lighter than water. Air wants to get above water, and so bubbles go up in water. Earth is heavier than water, so Earth is going to go down in water. And so there's a kind of natural place to each of the elements, a natural resting spot, somewhere the element wants to go, right? And that resting place is its end, is the end of its motion, right? Is the purpose of its motion, is its telos, right? So think back to the final causes of Aristotle. Well, the final causes of motion in earth, air, fire, and water is that they get to their resting place. Earth at the bottom, then water, then air, then fire. And so it's a teleological conception of motion because It explains why earth, air, water, and fire start moving. They start moving to get to their final resting place. Now, this terrestrial theory of motion was really challenged in a serious way by Galileo Galilei. And Galileo's thought was, look, it's not about how bodies start moving, it's about why they stop. And his thought, his fundamental sort of insight was the insight of inertia. What's inertia? Well, if you've taken a physics class, you probably already know the law of inertia says that a body in motion will stay in motion, and a body at rest will stay at rest until something interferes and stops the body in motion or starts motion in the body at rest. So that's what the law of inertia says, and the idea is, if this is right, it predicts that everything will fall at the same rate. So everything will move at the same rate, no matter whether it's made up of air, earth, or water, right? No matter what the proportions of the elements are, this theory predicts that everything should fall at the same rate evenly. So two bodies of the same size will fall at the same rate, even if they weighed different amounts. It's just that air works to stop the falling. So there's friction. And that friction works against gravity. And the differences in the rate at which things fall, Galileo claimed, is accounted for by the differences in the friction of the air on those bodies. I'm not sure he had quite a, I'd have to check and see if he had a developed theory of friction itself, but it was in that ballpark. It was in that ballpark. And the famous experiment that's attributed to Galileo Galilei, which is often it's apocryphal. It's thought that scholars have looked into this. They think he actually didn't do this experiment. The idea is Galileo climbed up the Leaning Tower of Pisa. Okay, maybe even a little leaning for the Tower of Pisa. There he is, Galileo. And he dropped two balls, a wooden ball and a leaden ball, right? So there's the wooden one and the lead one. And lo and behold, they fell at the same rate. And this was thought to be an incredibly damaging blow against the Aristotelian scholastic conception of terrestrial motion. Why? Why was this thought to be an incredibly damaging blow against the Aristotelian terrestrial conception of motion? Well, if you think about the four elements, and what something weighs is determined by the composition of earth or air or water in it, it seems like wood is going to weigh less than lead because there's less earth in it. There's more other stuff, maybe more air or more water, who knows? But that's what's supposed to explain why wood weighs less than lead. And because wood has got more air or water or whatever in it than lead or fire, it should go towards the earth more slowly than does lead. But Galileo proved that the wood goes towards the earth at just the same rate as the lead. And so it seems like the composition of the items, whether they're made of more earth, more air, more fire, or more water, doesn't actually matter for the motion. And so, in fact, it seems like these four basic elements don't determine motions in the way that the scholastics held they did. And so this was a great boon to the new burgeoning science of the scientific revolution, the new mathematical science. We'll discuss the new mathematical science more in the next video, but let me come back just for a second here to the final objections. So remember, we had this objection number 2 to Copernicus's theory. Well, why isn't it that everything doesn't fall off of the Earth? Well, if we believe in inertia and the air is moving around the Earth with the Earth, and we take a ship. This was another famous observation of Galileo's. We take a ship, and it's at sea. If you notice the ship going at sea, and you drop a ball from the mast of the ship, the ball doesn't go like this, right? The ball moves in this direction with the ship. And so from the perspective of the ship, it looks like the ball just goes straight down. So if you're on the ship and the ship is going 50 miles an hour, well, it looks like the ball basically goes straight down. Maybe it's blown by the wind a little bit backwards, but it doesn't want to fall, it doesn't sort of fall towards the Earth irregardless of how it was moving before. No, motion is relative. And in particular, the motion of the ball that you've dropped from the top of the mast of the ship is relative to the motion of the ship. So an observer on the ship is going to see the ball straight down, but an observer who's watching the ship go by, well, to that person, the fall of the ball is going to look like this, right? Because it's going to be moving with the ship while it's falling, right? So there it's moving with the ship, and in this direction, it's falling down. And so that really did a lot to explain why things don't just fly off the face of the Earth. But what about the accuracy of Copernicus's predictions? What about the third objection? Well, that's where Kepler comes in. So Kepler's idea was, hold on, Copernicus, what if the motions of the planets aren't circles, but are ellipses? Right? So what if the sun's at the center and then the planets move around the sun in different kinds of ellipses? That was Kepler's thought. And Tycho Brahe, shortly after Kepler, I might not spell his name right. I'm not even going to try. Tycho Brahe, I don't know how to spell that last name. I believe he was a Polish astronomer, made tons and tons and tons and tons of observations. So he made an incredible amount of observations and fine-tuned Kepler's theory and really, really honed it in and argued, yeah, Kepler and Copernicus are exactly right. The planets move around the sun in ellipses, and now with all of these observations, I can predict with as much accuracy where the heavenly bodies are going to be in the sky, with as much accuracy as the Ptolemaic theory could. And so it was then at that point that both the physics of the celestial sphere and the physics of the terrestrial sphere, the physics of the heavenly bodies and the physics of things on Earth that was put forward by the scientific revolution, it was really then that on both fronts, the new scientific revolution had a contender, right? I mean, it really could stand up to the old scholastic Aristotelian conception of motion. And in the next video, we're gonna be looking at some of the core tenets and doctrines of the new theory.